Good morning to you all. It's Tuesday, 18th of December 2012. We're going to have a look at mechanics of motion in preparation for the AS January PE exam. I'm going to start off looking at Newton's laws, a topic, of course, which you should already be very good at because you're studying this within your biomechanics in the second year. But just to remind you, we need to look at Newton's law 1, the law of inertia. And what we're looking at here is objects that are moving with constant velocity or indeed are in a state of no motion. So if we look at this performing the sprint start, we would describe this sprinter as having zero net force. And when we say the sprinter is in zero net force, that means that the sprinter will continue in this state, motionless, unless an external force acts upon them. So in this case, then pushing off the ground to accelerate forwards. But at the moment they are in a state of inertia. The total forces acting on the body are zero. And now we have a look at Newton's law 2, N2, the law of acceleration. In this law, we state that a body will accelerate proportional to the size of the force acting upon that body, and will do so in the direction of that force. So in our example here, we can actually see that Bolt is reading, as he pushes out of the blocks here, 226 watts. So he will accelerate forward at a speed proportional to that size of the force. Therefore, the harder we push, the faster we go. It makes perfect sense, of course. The harder we push, the harder we hit, the harder we throw, the further or faster we travel. We must also say, to get our second mark for Newton's second law, we must also say that the acceleration will take place in the direction in which the force is acting. Of course, Bolt here and Gay, Tyson Gay next to him as well, they have pushed backwards on the block, creating a reaction force upwards and outwards, and therefore the sprinters accelerate upwards and forwards in the direction that the force is acting. And thirdly, we have Newton's law 3, the law of reaction. Now, some people find this one a little bit tricky to get hold of, so I'll try and explain this nice and clearly. We are arguing here that as the leg, or in this case the foot, applies a force, and I'll actually draw this on with the use of a couple of vectors, as the foot applies a force backwards and downwards on the block, and of course you guys know from AT, you don't necessarily need to know this for AS, but we'd call this an action force. Not required for AS, but just in case. We have an action force acting backwards and downwards. We know how big that action force is because that's represented by the size or the length of the vector. We, of course, have an equal and opposite reaction force. In this case, a block reaction force from the block onto the foot. So, the reaction force is equal in magnitude, the arrows, the vectors, the same length, and is opposite in direction, and this is consistent across all actions in sport. So the foot applies an action force to the block, and the block provides a reaction force equal in magnitude and opposite in direction to the foot, propelling the performer forwards. Well, that's all fine, James. You might say to me, I understand my Newton's laws, but what do these laws actually produce in terms of types of motion? Well, here's our first type. It's called linear motion. First of all, we must be able to define what linear motion is, so get your pencils ready. Linear motion occurs when all parts of a body move at the same speed, in the same direction, at the same time. And of course, we have here an example of a skeleton bob. In fact, we have Amy Williams, gold medalist from the last Winter Olympics, who of course propels herself down the ice track, all parts of her body moving at the same speed, in the same direction, at the same time. So therefore this is an extremely good example of linear motion. In your exam you might want to use the term toboggan, because that's what tends to be on the mark scheme to get you a mark. A toboggan, luge, skeleton, bob, bobsleigh, these are all examples of linear motion. The other one we use is the flight of a shot put. And we actually argue that linear motion occurs in a straight line or a curve. So in this example, the curved shape of the flight path is still linear motion, and we can use that as an alternative example. We also need to know what causes linear motion, and you guys know already, don't you? But you must say that we cause linear motion by applying what is called a direct force, and that is a force which goes straight through the centre of mass of the object. So there we go, 3-mark question. Linear motion, all parts of the body moving in the same direction at the same time at the same speed, caused by a direct force, which is a force which acts through the centre of mass. Examples: luge, skeleton bob, bobsleigh, or the flight of a shot. And next we move on to angular motion. Angular motion, here comes your definition, same theme you have within this, but angular motion is when a body or part of a body moves in a circle or part circle. So we see here in the case of our skater who is performing a spin, the skater is spinning around their longitudinal axis in that direction, I believe. So this is a spinning action. So this performer is moving in a circle. We need to understand what causes angular motion, and you guys know already, don't you? It's caused by an eccentric force. And an eccentric force is a force which is off the centre of motion. So not on the centre of motion, but away from the centre of motion. So we apply a force outside the centre of motion. In this case, the performer has applied a force to the ice through their skate. But of course they haven't done it straight downwards. Here, they've pushed here, causing them to spin. Interestingly, we can also call an eccentric force, those of you that are into your physics, we can also call it a torque, or a moment of force, which is when the force is applied away from the centre of mass. We can actually measure how far that perpendicular distance is, and that gives us a measurement of torque rather than force. Now we also get a mark if we say that we can combine these two types of motion. So if we say linear motion combined with angular motion provides us with a notion of general motion. Okay, and also worth a mark in your exam. And you might ask, James, what is an example of general motion? I'm not sure. Well, my answer to that question would be, a brilliant example of general motion would be something like running or a sprinting action. We can see here that the torso, this part of the body here, is moving in a straight line, all parts moving at the same time at the same speed. But the arms and the legs are actually moving in part circles. For example, the femur of this performer is here, but in a moment it's going to be here, in a moment it's going to be there. It's moving through a part circle. So therefore that is angular motion. So the legs and arms are moving with angular motion, the torso and the head are moving with linear motion. Therefore we would call this performance general motion, worth 1 mark in your exam. Give it a try. And finally today we're going to talk about the concept of centre of mass. Now I've borrowed a photo here of my Uncle John. He lives down on Australian Gold Coast, which you see him here pictured, just getting himself ready to do a little bit of surfing. It's a bit quiet today, but anyway, we can argue here that my Uncle John, his centre of mass, I'll do it in red, it's about here on his torso, on his abdomen I should say, and we are arguing that the definition of centre of mass is the point of the body which is balanced in all directions. We might also say it is the point of the body where mass is distributed evenly in all directions. And it's sort of an imaginary point. It's not real, but we kind of can estimate where it is on a non-uniform object like the human body. A uniform object like a tennis ball or a table tennis ball, that would be in the very centre of the ball itself, of course. So, a couple of things we need to know in relation to a concept of stability. Okay, what makes some objects more and less stable? Well, we're saying here that if my Uncle John stands up on his tiptoes, so this centre of mass goes up and the height changes, then he would be less stable. So we might argue that the height, or where the centre of mass is in vertical distance, affects the stability. And the higher the centre of mass, the further away from the ground or the surface, in this case the surfboard, the less stable the object is, and therefore the lower, the more stable. He could stabilise by lowering his position, for example. The second point is, what is the mass of the object? An object with a large mass has more inertia and tends to be more stable. So, In this performance, a heavier performer would be more stable on the board. Thirdly, we have to ask ourselves, what is the base of support? Now in this case, we can say, first of all, Michael Johnny has 2 points of contact, and that the base is quite wide, so he's in a more stable position. If he takes one of those bases away, that's not what I meant to do. If we take one of those bases away and he stands on one leg, of course, he's going to destabilise this position. So the larger the base of support, the more contact points we have, the more stable. We might link this to something like a headstand. A headstand compared to a handstand has 3 points of contact, 2 hands and the head, and therefore is more stable than something like the handstand, 2 points of contact and a smaller base. And finally for today, what about the line of gravity? Well, really simple one, this one, kind of perfect common sense. We're arguing that the centre of mass in this case, look, is directly above the base of support, and therefore this is a stable position. The line of gravity is above the base of support. If, of course, Michael John leans over to the left and the centre of mass leans that way, and in this case the centre of mass would not be above the base of support, he is likely to fall into those sunny, warm waters and be wet. And finally, we're going to apply all of this to the concept of a headstand. Well, first of all, we can argue with regard to the concept of height that if this performer, in this case this child, if they lower their legs, their centre of mass will go closer to the floor and they will be more stable. So we can coach that earlier in our headstand technique. Lower the legs makes you more stable. Mass we can't really influence in this particular occasion, but we can influence the base. We can make the 3 points of contact as wide as possible, therefore the triangle base is as large as possible. And finally, with our LOG, line of gravity, we can make sure that the line of gravity is above the base of support, and therefore to stabilise this technique. Folks, thank you for listening. I hope the revision's going well. I'll try and keep posting these sessions for the rest of this week and certainly over the holidays as well. Keep in touch. If there's any feedback you can provide in the sessions, I'd be very glad to hear it. Have a lovely afternoon and work hard.